So for this one, the agenda for today is to cover the transformation fundamentals. So namely like your translation, dilation, reflection type stuff. And then we'll have a look at how it can all be put together when you have to do or apply a sequence of transformations, not just having to handle them individually. Okay, I think everything should be good. Screen share's up. Yes. Cool. So the approach that I'll be teaching today will be using point notation. So you have some point xy and you're mapping it to some new point x dash y dash. So xy is going to be the initial point that you're starting with, and x dash y dash is going to be the new point that you end up with. The reason why this is an appropriate way of handling transformations is because pretty much any curve can be thought of as a sequence of points all connected by a line, right? A curve that draws through all of them. So whatever you do to map one point to another point can then be to be applied to the rest of the graph as well. These are the 3 steps you follow for applying any given transformation. We'll have a look at a few examples. So first up, dilations. So dilations are all about stretching the function that you have, either in the x direction or in the y direction. The typical wording that you'll have will be either along an axis or from an axis. Typically speaking, in the Cambridge book, you'll get from, and I've seen a few worksheets and some circumstances where you'll see along an axis. The keyword that's being used there is essentially saying in what direction are you moving. So for instance, from the x-axis means that you have your x, do I have an actual, I don't actually even have an axis, my god. Essentially it's going further away from the x or in the y direction, right? When you go opposite from x, you are heading in the y direction. I'll just get my phone out to show a picture. Cool. Okay, so if you imagine that we have an axis like this and we have some point, stretching it along that direction would be considered from the x. It's going away from the x, but as another way of describing that would be to say along a y. If you're going to default to 1, you would probably say from. That's just what every other textbook is using, but both is technically valid. Now, how do we actually apply it? So in all circumstances, doesn't matter what transformation you have, you'll start by identifying your x and y and x dash y dash equation. In the case of dilations, those are always applied as a multiplication on the variable that you're trying to dilate. So in this case, since we're going in the y direction, the multiplication is going to appear on the y. So we have a few equations. The new x dash, is just going to be the same as the old x. Nothing was changing there. And the new y is going to be a times the old y, where a is considered the dilation factor. Next step is some basic algebra. You're just going to rearrange in terms of x and y. And the reason why is because when you want to substitute your transformation into a function, your function is in terms of x and y, not in terms of x dash y dash. So we do this little bit of rearranging, and then that gives us our substitution. So we start with any y is equal to f of x, whatever that function is. Every y is going to be replaced with y over a. It's at this stage we can remove the dashes. Those are more so we can keep track of what's going on rather than anything else. And then a further bit of rearranging just so we can get back into y equals f of x form like we're already used to for any other function. You'll pretty much always have y on its own when you're expressing a function. If your a value is greater than 1, so as it increases, you will stretch further along the y-axis. If you're getting closer and closer to 0, you'll actually experience it to shrink along the y-axis. So when you multiply by like a fraction between 0 and 1, that's the same thing as effectively just dividing by that number. Let's see an example. So we're trying to apply a dilation factor of 2 from the x for the square root graph. From the x means it's going in the y direction, so the dilation factor is going to be on the y variable. We set up our equations, we do our rearranging, and then we just do our substitution. And in some cases, you need to do one final rearrangement. This is going to look rather excessive for a very simple example, but it'll become much more useful when you have to then do it with a whole sequence of transformations back to back. Any questions so far as to how that's all worked? This is also a dilation, but in the opposite direction. In this case, we're going along the x or from the y. So the multiplication is going to be on the x. Everything else looks exactly the same. One thing I'll point out here is because this is already in y equals f of x, there's no further rearranging to actually be done here. And so one of the interesting things we find is that a dilation factor in the x direction is going to actually appear in the function as a division symbol rather than a multiplication symbol. So it's a bit weird in that regard, but hopefully seeing these steps outlined as they are will give you a bit of an appreciation as to why this looks the way it looks. In fact, when we have a look at translations, you'll start to understand a bit better as to why x minus a value shifts it right, when normally plus should be right and minus should be left. You'll start to see a bit of like why that's the case. This is basically the exact same example, except the multiplication of the 2 is on the x. And again, as you can see, now the x over 2 looks like it's a divide by 2. It is a divide by 2, but the way you would express that is a dilation factor of 2, specifically from the y-axis. Fair enough on why those are looking different? Cool. Reflections. So reflections are always just the application of a negative sign, either on the x variable or on the y variable, depending on which reflection you have. Reflection in the y-axis or in the x-axis would be the key terminology that you're using there. The axis that you're mentioning, the way to think about it would be as if to say that axis is acting like a mirror. So if I go back to the axis that I drew up earlier on the document camera, and we have that same point, we have a reflection in the y-axis. So if I pretend that this y-axis is a mirror, then the reflection of that dot would be now over here. Right, it's reflecting in that axis. Now, when you look at where these two dots are located, horizontally speaking, or I guess I should say the height of them is actually consistent the entire way. This y value is the exact same as this y value. But what's different is the x location. This is some positive x and this is some negative x. So when it comes to putting the negative sign on a variable, the one that's changing is the x, hence we're putting the negative sign on the x specifically. So if we go back to the pre-written notes, it's basically the same as dilations, except you're putting a negative sign instead of a number on the variable. The rest of the steps are exactly the same. As for how that might look when you have, like, for instance, multiple variables, you're essentially just replacing every x with a negative x. And in some circumstances, that can obviously be simplified. For instance, when you square it. Any questions about that?
Chris, sorry about that. You just sort of cut out. I don't know if that's a problem on my end. Could you just go over that again?
I cut out, yeah. I cut out around the example or the description of reflection. Maybe I'm cutting out again.
I got the like reflection part, but not the example.
Oh, sure. Okay. Cool. So for the example, I was just describing, like, let's say you have multiple x's in the equation. What you're essentially doing is replacing every x with that negative x. Right. The steps are pretty much all the same if you want to go through the whole procedure. But as far as like a shortcut will be considered, if you already know you're putting a negative on the x, then you're just replacing every one of these x's with a negative x. Cool.
And then shouldn't it be negative 2x squared minus 3x? Or
so that's a good distinction to make. You're replacing specifically the x. So when you think
oh
about the fact that the square is only on the x,
yeah,
that's why it's only going in there.
right, yeah, my bad.
Good. Reflection in the x, again, the way to think about that is to now think about the x-axis as the mirror. So again, maybe if we go back to the picture, in this case, if you have that same initial point, now the x is going to be the mirror. So you dot, 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 reflect it down there. You'll notice the x values aren't changing. It is still vertically, it's still along the same x value, but what's changing is the height. The y has gone from being a positive to a negative number, which is why the negative sign is going to go on the y instead. And so back to the notes, you'll see if you go through the whole procedure, you'll put a negative on the y, and then you'll pretty much just chuck that back over onto the f of x, because again, we want to have y on its own. So yeah, in pretty much all these circumstances, I show you the shortcut at the very end, especially useful for these simpler examples where you don't really want to go through 3 lines of working just to note, yeah, I just got to chuck a negative on the thing. So all these little highlights in green will actually be summarized at the bottom of these in here. And so you can see what all those shortcuts look like. But as for a quick application, yeah, so you go through the steps, the negative ends up on the y, you put the negative on the y, and obviously, well, that's just algebra to get the y back on its own. Translations. This is the one that I sort of mentioned earlier, which is the difference between like y, x minus a value, shifts it right. And the reason why is because we use this point notation approach to apply transformations. So it is indeed the case, if you want to shift something right, you do in fact want to plus on that x. Right? You're starting at some x value, and you want to add to that x value. So the new x is going to be x plus whatever you're trying to shift it in the direction of. What changes is when you do the rearranging to get the x and the y. So it's the fact that you're trying to shove it back into the function, which is why things are reversing, specifically in the x direction. And so instead of having your y equals f of x, you replace that x with your x minus a, and suddenly, even though you started with a plus, it now looks like a minus. That's just a bit of trivia as to where it's from. As for the application of it, again, if you're just doing basics, a shift left of 5, you would already know just from polynomial stuff that you just replace every x with, well, since it's being shifted left, it'll be x plus 5. But if you go through the procedure, that'll explain a bit more as to why you're doing that. You start with the x minus 5 because you're trying to shift it left. When you rearrange, it becomes the plus, and then that's why it's being subbed in. In this case, I've elected to expand it. Seems like you could also do a factorizing approach, taking out a common factor of x plus 5 at the front, and whatever that looks like would also be applicable. Yeah. Vertical translation's a lot easier. Nothing's really changing. Even though you do flip, you kind of get a double flip going on over here. So it starts as a plus because you want to shift the point. It flips to a minus because you want to get the y on its own. But because the y is already on the left, when you shift it back over to the right, it just sort of ends up back where it started. So that's why typically the y transformation stuff is intuitive, whereas the x transformation stuff, you kind of got to flip your brain a little bit. The shortcut of this is super easy. You know, we're trying to apply a vertical translation of -2, you just slap a -2 at the end. Or, of course, there's this whole procedure to tell you why you do that. Those are all the fundamental transformations. Is there any one of those I should explore in any more detail? Because we're about to go into how to do basically all of them back to back.
Chris, is there any example where we have like multiple translations in one?
Yeah, so you'll typically get like a vertical and then a horizontal, or the other way around. You could have them back to back, or like, I mean, it's rare, but it's not necessarily impossible to be like vertical translation, dilation, vertical translation. It can be done, but usually the way the questions are written, they want to test and see you know all the key types rather than just sort of doubling down on things, just from a question writing perspective.
Yeah.
Haven't seen it, but it's technically doable. Yeah.
Okay.
But okay, cool. So we learned this extensive process. Now we're going to see why you would bother with it. So all we're going to do is essentially be repeating that this initial step of trying to figure out what's your new x and what's your new y until you get through the full list of transformations, and then you move on to that step 2 of rearranging for your x and y, and then finally the step 3 that we had before, which was subbing it back into the function that we started with. So let's have a look. So one of the things I'm going to highlight here is that the order in which transformations are done actually does matter a lot. You can't just take for granted each of the individual bits and shove them in whatever order you like. We'll see an example as to why. So these are the exact same transformations, but they're done in a different order, and you'll see the end results will end up looking slightly different to each other. So how do we handle this? Well, we're just going to go one transformation at a time. The first one is a dilate factor of 3 from the x. Now, reminder, from the x means it's going in the y direction, and because it's a dilate, it is a multiplication. So you start with your initial point xy, and it's now going to become x comma 3y. Dilate factor of 3 has been applied. The next thing that was mentioned was a reflection in the x-axis. So once again, the x-axis is the mirror, so the thing that's actually changing is the y. So the negative goes on the y variable. Now, one thing to highlight is that you always start the next transformation application where you left off previously. So we're now starting at x comma 3y and then applying it to that. And lastly, we have a sequence of transformations here, translations rather. So this is a translation of 5 in the positive x and 1 in the positive y. So that's the more typical example of where you'll have two translations back to back. There'll be one in the x and one in the y. And so again, starting where we left off, translate 5 in the positive x, you slap plus 5 onto the x. 1 in the positive y, you slap the plus 1 onto whatever you had previously. And yeah, this bit here would be your x dash, this bit here would be your y dash. Then you would just sort of go from there and shove into your f of x function, whatever that is. I've done this so many times and I've still not bothered to put the actual follow-up on that. So let me do that live right now on the handwritten bit. So what that would now look like is we would say x dash is equal to x plus 5, and the y dash is equal to minus 3y plus 1. That gets us our x dash y dash. The next step, once you have the final version of that, is to get your x and y on its own. So you're going to have x is equal to x dash minus 5. Yeah, x equal to x dash minus 5. And then y dash minus 1 equals minus 3y. Y is equal to minus y dash minus 1 over 3. And you can refactor that however you like. It's not going to really matter too much because we're going to try and shove that into y equals f of x. So every x is going to be replaced with the x minus 5, f of x minus 5. Every y is going to be replaced with all of that. So that'd be negative bracket y minus 1 on 3. Again, remembering that we're just going to knock off those dashes. Those dashes were only there for us to keep track of what's going on. This looks nothing like a function, so we're just going to rearrange it until it does. So chuck the negative and the 3 over and plus the 1. Y equals negative 3 f x minus 5. And then after those have gone off, we can chuck that plus 1 over. And so we can see we have a reflection, we have our dilation, translate, translate. And that's what basically any f of x would look like if it was subjected to those transformations. Any questions about that one? Cool. Back to the pre-written notes. The transformations we'll look at are going to be the exact same thing, but in a different order. So in this case, we did translations first. So you start with your xy, you put your plus 5 and your plus 1, kind of like what we did at the end at last time. Here's where things are going to get a bit different. Reflections and dilations are both multiplications. And one of the things that you have to keep in mind is when you're applying multiplications, you've got to apply it to the entire thing in that spot. So for instance, this reflection in the x-axis, we know it impacts the y. It doesn't just impact the variable called y, it impacts the entire spot that the y goes in. So when you put that negative sign on there, it's actually got to impact both of these things at the same time. Same thing with any other multiplication. Dilate factor of 3 from the x. From the x means it's hitting the y. And so again, when you look at these two things, they're not that different. They're both still going to, when this is expanded, have a negative 3y. But this plus 1 over here would now look like a negative 3. So a little bit different, but all that's there is to highlight that the order in which you do things matters. Do it in the order that's been presented to you. Yeah, that'd be the only real major thing to worry about. It's a pretty repeatable process. You just do this every single time, and as long as you've got that procedure down pat, you pretty much never get these wrong. There are other ways to handle it. This is the way the book has presented, and it was actually a way that wasn't taught to me in school, oddly enough. And I find this one to be probably the easier one to follow. You can kind of do it just by by recognition, where you're like, okay, I got to apply the f of x notation stuff, kind of like these, right? Just using a sequence of these back to back. But at least when I was in school, I would get a bit lost doing this. Yeah, that's it for the lecture portion. Are there any questions that I should clarify before we get into the textbook stuff? Awesome. So do we want to jump into the individual transformation stuff, or should we go straight to like applying them all back to back? It's a very similar procedure either way, but I'm curious to see where we should probably start. Any preferences? All right, let's go straight to the fun bit. So cool. Anything, so from chapter 3 on to C is basically the individual transformations. You do your translate, dilate, and reflect. 3D is where you're going to do the sequence of transformations. So, okay. This is where we'll start. Do you guys want to have a stab at doing these yourself, or do you want to go through them live together? At least initially. There's no preference, feel free to have a stab at it, starting from question 1. So you're trying to figure out the rule, so the function. You'll see this key wording like of the image. Basically, that just means find the rule after the transformation has been applied. These are the transformations, and these are the functions you're applying them to. We're not going to do all of this. This will be a lot. So let's just say we're doing AI. So you want to take this sequence of transformations and put it into this x squared quadratic. And while you guys work on that, I'll get the classwork doc up. That way you have some homework recommendations to follow up with. Yeah, I think this is the right one. Quadratic's probably a good one to start with too.
Chris, is
Yep.
it y is equal to x plus 2 squared minus 3 all over 2?
Yes, this is what I was saying. Quadratic. I was about to say quadratic would be a good one to test on because we actually already pretty well know what a quadratic should look like. Like for instance, if you imagine just sort of what you would think the quadratic would look like, a translate 2 in the positive x, you kind of already know that should look like an x minus 2, and the 3 in the negative, you know that should kind of look like a negative 3. So these are kinds of things that you can do to error check yourself if you already know what the function roughly should look like. If some of the terms don't look right, then you can go back and check things. Now, what's likely happened is this dilate factor, I think you put on the wrong term, and this I think you've got. So maybe you didn't do the shift to x and y, the rearrange after the x dash y dash. That might be the thing to have a look at. Actually I'll quickly just get a photo of these so you can see the steps quite clearly there. Should be coming through soon in the chat. Add 2 bracket x plus 2 squared minus 6. Still seems a touch off. Yeah, okay. Maybe I'll just go for this one live. Unless, Raquel, are you close to a solution? Not quite? Yeah, okay. Had a feeling we might have to go through at least a few together. Okay, so let's debug things. So we're going to start with our xy, always. What does the first transformation look like when we get our x dash y dash? Dilate factor of 2 from the x. What would that now look like?
X comma 2y.
X comma 2y. Let me just double check. Looks like from the x means it's in the y direction, so the y should get its factor. Yeah, precisely. X comma 2y. Alright, next one up. What's that going to look like? Translation 2 in the positive x.
X plus 2 comma 2y.
That's it. Yeah. Translations are an addition or a subtraction. So you got the x plus, what was it again? X plus 2, comma 2y. Again, leaving off from where we left, starting where we left off. And last one up, 3 units in the negative y. Translate.
X plus 2 comma 2y minus 3.
Perfect. X plus 2, 2y minus 3. So this is x dash, this is y dash. So when we have our equations, right, in equation form, we have x dash is x plus 2, y dash is 2y minus 3. So if we take a quick step back and have a look at like the step-by-steps, we have done up to step 3. Right, we identify what the first transformation is, we did the next one, and then we did it until we finished all of those steps. Step 4 tells us to rearrange to get x and y on their own. So what's that going to look like?
X is equal to x dash minus 2.
Yep, x is
and
x dash minus 2.
Y is equal to y dash plus 3 all over 2.
Y is equal to, yeah, y dash is going to get the plus 3 and then all divided by 2. Yep, perfect. All right, that's what step 4 said. Step 5 says substitute the new x and y into f of x. So in our case, we had y equals x squared. That was our function. So this is our starting point. How are we going to make step 5 happen?
We just sub in the new values.
That's it, yeah. So we've got this thing called x. We know it's equal to that, so we put that in there. We got this thing called y. This is also our y, so we put that in that spot. Y plus 3 over 2 is equal to x minus 2 all squared. Remember, the x is squared, and so because you're replacing the x, everything is now going to get squared there. It's not really on the list, but you do have to also rearrange this as well. So you're going to have y plus 3 is equal to 2 bracket x minus 2 all squared, and then, well, yeah, x minus 2 all squared minus 3. This is just a turning point form quadratic. So what I was kind of saying as a bit of like an error checking method is you can now look at your answer and be like, does that make sense for the procedure that I've got here? Dilate's a bit hard to see because you've got to remember the difference between like if it looks like a multiplication or a division. But with the translation stuff, that's probably the most intuitive, which is like, okay, 2 units in positive x. I know quadratics should be like x minus 2 to achieve that. 3 units down, I know that should have a minus 3 on there for quadratics. So you can use this end result to be like, cool, did I actually get a function that makes enough sense?
Chris, just a quick question with the turning point form.
Yep.
Isn't it like meant to be like the multiplication factor of 2?
Yep.
Isn't that also meant to like apply to the negative 3 when you have it there, or it doesn't work?
Well, here's the algebra. So because the 2 is dividing both the 3 and the y, you would multiply the 2 first, and then the subtraction of 3 would come afterwards.
Okay. Let's say if the 3 came first, then like...
Yeah, so if you had, the way that would work is if you had like plus 3, I'll just redraw this whole thing. So if you had y over 2 plus 3, then yeah, what that would now look like is you would do your minus 3 first, so x minus 2 all squared minus 3, and then you'd be left with that multiplication of 2, so 2x minus 2 all squared minus 6. Now, this is kind of why I like this procedure, because it's actually just algebra. You can then see the steps quite clearly, whereas when you're just sort of looking at the function like substitutions the entire way down, it can be a bit confusing as to does this 2 impact the translate or does it not impact it? When it's just algebra, this is stuff you guys have done forever. So it's hopefully a bit easier to do it this way than if you were just doing the whole look at a bunch of f of x substitutions.
All right, thank you.
No worries. Yeah, in fact, I'll touch on a bit just to show you the difference, the other approach. So if I were to just do a sequence of those sort of f of x shortcuts, I'll just quickly show what I mean by that on the screen share bit. So I'm talking about like these y equals a times f of x, x over a, all these sorts of things, right? All these shortcuts. It's still the same sort of idea where you want to apply everything in a sequence, but you're kind of just going straight into the function. So you have your y equals x squared. The first thing you have is a dilation factor of 2 from the x. We know that impacts the y, and that looks like this, right? That's the shortcut, which is any dilate factor that impacts the y just goes right at the front of whatever you currently have. Then from there, it was a translate of 2 in the positive direction of the x. In transformations land, we know that's an x minus factor. So we have y equals 2 bracket x minus that translate factor. Remember, we're replacing just the x with that shortcut. And then lastly was the translate 3 down, which we know is you start with whatever you have, and then you put that translate at the very end. It doesn't look hard, but it's this sort of stuff where you start sort of getting a bit, well, where I personally started getting confused, which was, hang on a minute, when I have this translate at the very end, does it get impacted by the till or not? The answer is it doesn't, because in that particular order, when you're doing it in that sequence, you always leave off exactly where you started. Whichever of those approaches makes the most sense for you, feel free to use it, right? I've done what I think is the easier one to follow, but there's two ways of doing it, and if you like this better, by all means. I'm not going to force you to do either way, and neither will the textbook will kind of give you some stuff where you have to still at least be aware of the x and y dash stuff. They don't have it in this chapter. Where do they have it? They've got it somewhere in here. I know they've done some x dash y dash stuff. So be at least aware of it if you're going to use the other method, but again, either way is going to be up to you. Anything to clarify about maybe that approach? Cool. Should we go through another one together, or do we feel confident to try and give, let's say, B double I an approach, a go? So it'll be this cube root, and we're applying the transformation set from double I.
Chris, is it going to be y is equal to the third root of x over 3 plus 2 minus 4?
It'll be, so is the x plus 2 the entire numerator, or is the plus 2 off of it?
The plus 2 is like outside of the fraction here.
The answers say that it should be in there with it as well. Everything else was fine. Maybe just double check your working to see if that's actually the case. Because, sometimes the answers get a bit wrong here, but they've got it included in the numerator.
No, I'm pretty sure that like it should be like the 2 should be outside the fraction.
Okay, sure. Let's have a look then. Raquel, are you close to an answer?
Yeah, but also at what point do you drop the dash from the x and y?
So the way to think about it is the dashes are just there so you know what you're putting in where. So the dashes just say this is the new bit. I drop them off immediately after the substitution. So you start with your initial function, whatever it is. In your case, it'll be the cube root x. You replace every y with whatever you got. You replace every x with whatever you got, and at that stage, you just ignore the dashes. But okay, cool. So while you finish that one up, walk me through it. So how'd you go?
You asked me.
Yeah.
Okay. So first we got xy.
Yep.
Then we got 3x comma y.
3x comma y. Yep. 3 from the x.
Right, and then we got 3 bracket x minus 2.
3 bracket x minus. Let me see. Translate 2 in the negative. Yep. Looking good.
And then y minus 4.
Y minus 4. Yep. 4 in the negative y.
Yeah.
Awesome.
So then I got y is equal to y dash plus 4.
Yeah, let me just catch up real quick. So y dash, y minus 4, x dash, 3x minus 2. Yeah, so y would in fact be y plus 4. Whoops, y dash plus 4.
And then I got x as x dash on 3
X dash on 3. Oh, yeah, okay.
plus 2.
Yeah, that should definitely be outside. Let me think again. So divide by 3 plus 2. Yeah, they stuffed up. Answer stuffed up. Cool. So that would then be, you've got the y is equal to cube root x, unless they did something weird with that. No, it's just standard cube root x.
You know when we've got x dash is equal to 3 times x minus 2, is it like possible you can expand it and then that might make it easier, or you don't want to do that?
Is it possible to expand? Yeah, it's fine to expand it. You've still got to get x on its own though.
Yeah.
So that sort of makes it slower.
Okay.
But otherwise, yeah. I mean, you'll still get to this point either way, I suppose, is the answer. But yeah, so this will get your y plus 4. This will be the cube root, yeah, x over 3 plus 2. You'd probably want to put this over same denominator at some point. So you'd have your cube root, what's that, plus 6. And then the minus 4 at the very end. That's what it should say. Oh, I just realized it's going a slant there. Whoops. Yeah, answers had that one a bit off. Cool. Yeah, any questions about how that's going to be? Awesome. All right, we'll keep going. We'll finish off, I guess, C triple O. We'll keep the pattern going. We're doing this truncus and yeah, there's a bit less going on. This is just a dilation and a reflection, which is the same, is the first time we've seen a reflection, so I guess it's worth having a look. C triple I. I should probably do this one myself as well, just to make sure the answer's got it fine. Do that.
Chris, is it 2 over x squared? Y is equal to 2 over x squared.
That'll be it. 2 over x squared. The negative was on the x, and so because it got squared, it's going to disappear. Yeah. Anything to clarify on those? Cool. One of the things that the textbook will do, more so than anything else, maybe a SAC might do, is these like things in question 2 and 3 here, where they give you a non-typical function and they ask you to now sketch that graph after having applied a sequence of transformations to it. I haven't really covered exactly how to do this. It would be closer to when you imagine doing like that whole f of x approach, where you use a sequence of shortcuts there, where you would effectively be rough sketching what these new graphs would look like for each of the transformations, using the previous one as your new starting point every time. A couple of key things to consider. You have some known points on the graphs. Those are good because you can very clearly know exactly where that point should end up. Like for instance, a reflection in the x-axis, the x is the mirror, and so while the x will be maintained, the y should now go to -3. So you know you're going to have that point down here, and well, this is already on the x-axis, so that's not going anywhere. -0 is still just 0. And so you kind of already have those 2 points. You can even just sort of use that to get your graph looking like what it should. So if I were to start using that approach, the first application of that transformation might look something like this. So I draw my 2, which is my turning point. The 5, 3 is now going to become 5, -3, which I'm going to pretend goes there. And the graph, let's see, so it would have to sort of concave downish, turn. That's horrendous. It'll be something like that. Yeah, it looks fine. Just reflecting the entire thing down since you're reflecting in the x. The next thing they said to do was dilate by a factor of 2 from the x. From the x, of course, means going in the y direction. But reminder, we're starting at this thing here. So shall we label this point 5 - 3. A dilation factor of 2 from the x means multiply all of your y values by 2. The only y value that we have that's like right there for us is that -3. So that's now going to become a -6. And that's a 0, so that's still going to be saying a 0. So realistically speaking, because we get to set our own scale, it's going to look basically the exact same thing, but I'm just going to put that as a 6 instead of a 3. The shape's still going to be identical because it's all being dilated in the exact same way. What's changing is the scale of it. Translations, however, will force me to do something different. So translate 3 in the positive x and 4 in the positive y. So we have a couple things to look at there. So let's start with that initial turning point there. If that's being shifted 3 in the positive, it's going from 2 to now at 5. And 4 in the positive y means that turning point is now going to be up here at 4. It's going to be a turning point. Just a quick little sketch to remind myself that's what that is. And we had the other point, which is now sitting at 5, -6. It is also being shifted right by 3. So we've got 5, 6, 7, 8. And this is being shifted up by 4. So it's going to go from -6 to now -2. The other point. And just try to maintain that shape again. So still going to bow out like that. The shape of it isn't really changing because it's purely translations. Actually, this is an asymptote. That's going to come with it. Yeah, asymptote's a bit hidden there because the asymptote was on the y. There was a hidden feature, which was this has an asymptote of x = 0. that is also going to be impacted by the translation right. So because it's being shifted right by 3, it's now going to asymptote at 3. It's not exactly told to us it's an asymptote, but it definitely looks like one, so we're going to treat it like one. It's kind of hard to tell if it's on an axis because you don't label it if it's on an axis. And yeah, that'll be that. That's the overall procedure. You just draw a sequence of graphs back to back using the last one that you left off with as the starting point of the new one. Pretty rare that you'll have to do that in an exam anyway. The book does it, and a SAC might do it. Any questions as to how we did that? I reckon if we do question 3, it might take up all the time. So before we do that, I'm just going to see if there's anything special here worth touching on, just in case. This is just the same as the stuff we had done before. It's just these again, but instead of having like 2 transformations, they give you 3. Whatever. It's just one more thing to do an XY. And they really packed in a lot of things to do here. Like doing 4A means doing all of these for A. Doing 4B means doing all of these for B. It's nuts. So when you're doing these yourself, unless you're still struggling with it, don't do everything. You don't need to do all of it. Just do enough of it to where you're like, yeah, I'm not going to get these wrong ever again. Same. And this is just telling you to sketch, but like, sure, if you want to practice your sketching of these functions, go wild, but more importantly for this chapter would be the transformations. Okay, that should be fine then. Cool, let's see if we can smash out question 3. So, exact same idea. The graph is worse, I'll say, but try to do the application of it. Just remember, what are the key features? So we're talking the asymptote, the origin, the 2, 3, and the 4. Those are all the points I'd be watching that would transform as I would know exactly where those are going to go based on the transformation. And then you just do your best to curve it along with it. And at the end, we'll show you what the picture, what they drew as the picture.
Is there a point at 4, 0, or is it just to the right of 4?
Is that 4? Yeah, so they can look a little bit off. The intention is that's going to be 4, 0. Yeah.
Okay.
Like this one, if you zoom in, isn't exactly on the. I don't know. It's like a mix between them hand drawing it and it's digitally. I've had this conversation so many times. It's slightly tweaked off. Yeah, that was a fun one. I was drawing it alongside you guys as well. How many transformations down are we? Getting close?
I'm trying to figure out the last one.
Last one? Yep. Okay, well, that's good. There's only one thing left to do. Dilate factor
But
of 2.
I just want to check if my graph is like okay.
Hmm.
So obviously like the reflection of the y-axis, like it just reflects like sort of like I don't know how to explain. It's
Yeah,
like
yeah. That's why I was
it's
going to
in
show
the
the
page
picture
above.
at the end, but yeah, I've got my version of that here. So that's that first one. That's what you have for the first one ish. Maybe. Uh-uh.
Yeah, so that's what I had for the first one.
Oh, okay, good.
Yeah, and then the second one was like I did like both the translations in one.
Oh, yep,
So yeah, my like the turning point went down to yeah, -4, 0. And
yep,
then the other turning point was at -2, -3.
yep.
And then the asymptote moves like to the y-axis.
Hmm.
Oh wait, no, sorry.
Oh,
Is
yeah,
it?
the vertical, yeah,
Yes.
vertical asymptote is the y-axis. Yeah, yeah.
Yeah.
This one,
Oh yeah, and
yeah,
that shifts
yeah,
down.
horizontal as well for the x minus 3. Yeah, I should have drawn that in as well. I was just kind of
All right, yeah, yeah,
speeding
my
it.
bad.
Yeah, there's this other point out here as well, the -6,3, just keeping track of that initial 2,3 point. But yeah, that's that one. And then the final would look like this, which is just, multiplying those x's, of course.
The 6,3 point, where does that like come from?
That was initially 2, 3. So 2, 3 flipped to negative. Oh, so hang on. No, this was the 4, 0. So 4, 0 flipped to -4, 0. Then with the translation, it shifted 2 more to the left, and it shifted 3 down. So that was the
Yeah.
x-intercept that we started with.
There's so many numbers like doubling up. Like
Yeah.
too many twos and threes and too many fours and zeros. Just
Yeah, yeah. Like I started drawing this with just the dotted lines and the dots, and then I
yeah,
got to here. I'm like, shit, I have no idea how to draw this graph. Let me just go back and do these curves. Okay.
yeah.
Because I was like, yeah, I'll speed things along and just get the dots in. No, you need a curve. But yeah, like this is kind of why it's not in a sack. There's only so many marks I could allocate to this, and I don't want you like that one. That took me. How long was that? I think we started like I think it was 6 minutes. Surely not
Yeah.
6 minutes, but
Long time.
yeah, it's a long thing, which is why it doesn't really show up. Because otherwise, I'd have to give it a lot of marks, right? If you think about 1.5 marks per minute, it's well, yeah. What's that? 9? A 9-mark question to do this. I'd love that. But yeah, so that's the hardest it'll have a look if you get it. But highly likely that you don't. So don't feel too bad if that's still a bit of a challenge. But okay, so I guess to recap, it seems like for the most part you guys are at least pretty strong with getting your x dash y dash stuff. Like you'll know how to start with x, y and get all the way to your final x dash y dash. Where things were kind of getting a bit rocky was when you sell it back into the function. So I think based on that, staying with 3D seems fine because anything from earlier is just going to be simpler versions of the x, y dash stuff that you already know how to do. I guess the substitution would be a bit easier, right? There's less going on, but I feel like you guys are at the stage where you could probably handle the algebra for these. So yeah, try as many of these as you can. If you're still getting them wrong on a regular basis, just hop back to the previous chapters and do the individual ones, and then work your way up to this. But the only difference between them would be just how much algebra is going into it at the end, not necessarily the actual procedure you follow. Yeah, next time we look at this, we'll be doing it in the reverse direction. You've got a transformed function. How do we get back to a baseline original function? I'm happy to stick around for a little bit if you have any questions. Otherwise, enjoy the rest of your night.
Thank you.
Thank you.
Thanks.